I come from the University of Eastern Finland, and currently I act as a professor in biological spectral imaging. UEF does not actually pay my salary. I'm funded by a private fund, and they gave me 300,000 to 400,000 euros and said that do something useful. I cannot hurt small children and those kind of things, but basically I can do whatever I want in here. And I have chosen that I would do some research that is basic research, but also applied research in the field of forestry and wood material science. Now, we start from here. So tree nurseries, they are producing like hundreds of millions of small tree seedlings every year. And everything just looks quite fine over here. But as soon as you put them out or even inside, something always goes wrong. Now, this is of course economically important, but it's also, it would be very, very useful if we could have ways to look at the plants before the damage is actually really happening. And that would save a lot of time, labor, and money. And that is actually called phenotyping. And our laboratory is part of a national Finnish plant phenotyping infrastructure that is a shared infrastructure between University of Helsinki and University of Eastern Finland. And then we have collaborators at University of Turku and Oulu, and also Natural Resources Institute Finland, which is not located in Norwegian Sea. But, and by the way, those small light spots in the sea are actually oil drilling rigs, and they are burning the excess natural gas, and you can see it in the satellite image. Now, what we do is that in Helsinki we have these kind of facilities. There are 2 automated systems for plant phenotyping, meaning that we are looking at plants non-invasively, and we have quantitative information that human eyes may not be able to see. And this is used for many, many purposes, and you can also use it for tree screening, and they do that actually over there with different kinds of techniques. And in the image on the right you see there's an imaging chamber and an automated system where the trees are going there to have imaged. Our laboratory in Joensuu is this, so we call it the Spectromics laboratory, and we are focusing on specific techniques. We are not a high throughput laboratory, we are low to medium throughput, but we try to look at things in more detail. And one of the major technologies that we are actually utilizing is hyperspectral imaging. And we have these line cameras that were mentioned in the earlier talk. So it's not a frame-based system, but rather they are like scanners. We see one line at a time. We have three imaging stations, altogether 4 cameras, and they cover an exceptionally wide range of electromagnetic radiation. And I am actually not aware of any other, at least a plant laboratory in the world, that would be having this wide range of spectral cameras. What we have here is in the middle, we see 2 cameras manufactured by Spekim in Oulu. There's a Venir camera for the visible and near infrared from 400 to 1000 nanometers, and then a shortwave infrared up to 2.5 micrometers. And then on the right-hand side, there's a thermal image of a quite specific instrument. There's an imaging station for thermal range 3 to 5 micrometers, mid-wave infrared imaging. So not thermal imaging, but rather spectral imaging in the thermal range. And then apparently, currently the only manufacturer of a ultraviolet range spectral camera is an American Headwall, and this is the only one that they have sold in Europe. It used to be manufactured by Speking, but they have discontinued this model. Now, we have lots of other things in the lab. We had approximately 1 million euros, and with the promise that we will again buy something useful, and I decided to buy all of these. And basically this is cheaper than the earlier slide, but I will mention one thing over here that might be of interest, and I will show some results that are based on the specific technology of illumination. And we have this on the right-hand side. You can see that we have this very powerful xenon light source with liquid light guides that we can attach to a microscope or image macroscopic objects. And it's an angle tunable filter-based unit, so thin film, angle tunable thin film interference filters, and continuously adjustable from ultraviolet to the visible range, relatively narrow bandwidths, and specific cameras, and a very, very sensitive ultraviolet range camera that was specifically tuned for us. Hyperspectral imaging, we already touched that on the previous talk, but basically the idea is that we don't have 3 bands, but we have like hundreds of bands in there, and that's one Arabidopsis plant that you will look at the RGB camera or with a hyperspectral camera. And the result is a data cube, terabytes of data if you are doing a lot of imaging, typically gigabytes. And you have this data cube so that you can look at different wavelengths separately or then do other kinds of computational analysis. It's in vivo imaging. It enables so living objects, non-invasive, rapid, and effectively combines the spatial information with chemical information. This is a hand by Lord Foss, postdoc in our group, and this is just to illustrate that you can look at specific features which are on the surface of your object, or you can look also deeper. So on the right hand side we have a little bit longer wavelengths, and we can see the blood veins then from deeper in the hand than we do in the middle. Of course, classic example is look at paintings, and Sarita, another postdoc in our group, was not happy with the apples and painted this Ellen Teslev's copy of Kaiku over there. But when we put the painting over there, we can look at the underlying images over there. So what is it actually used for? Technology in forestry and basically plant science. So you can look at most often you look at the reflectance. You can have different wavelength ranges, different scales, even microscopy. We are doing that. That's difficult, but this is collaboration with the Japanese optic giant Olympus. And then we can look at spectral features that relate to something that is relevant. And most often people are looking at things like NDVI or something like that, and index-based imaging for that somehow corresponds to the plant health or condition in general. Those are based on chlorophyll absorption features, near-infrared reflectance. You can look at water content, and then, for example, nitrogen as a central nutrient, different kind of nutrient deficiencies. We have tried this, works quite nicely. And then also a special case is plant secondary compound accumulation that I will look a little bit more closely later. So generally speaking, there are many, many application areas in forestry. Precision agriculture and forestry is the one that is really sensor-based, where you have to have a lot of data that is real-time collected, and then you can do appropriate measures for your crop. Wood and biomaterial science, my examples mostly from there, chemical imaging, but you can also use it for different kinds of stress, or let's say we have an example of a carotenoid index or water content and so on. So stress characterization. One example that is often a goal in here that we have done, not published yet, but we did a study. This is not a tree, but it's a small plant that was exposed to cadmium, and with our own eyes or normal cameras we can see the symptoms of the cadmium stress in day 18, but if we are using a hyperspectral camera we can see the first symptoms on day 11. Some other examples that we have been using our cameras for, this was published in PNAS early this year. So basically these are peat samples, and we can then characterize them in quite much detail, and then further with the chemical details as well. And soil samples, we haven't really done the computation yet, but it appears that we can classify soil samples that are collected from different places and to have information very, very rapidly then, and you don't have to do the labor-intensive, the FTIR analysis. Our first publication was on spruce seeds screening, 2015, where we were utilizing these two main instruments, Veneer and SWIR cameras, and then something called kinetic thermal imaging technique that I will not go through here. But the main idea here is that we got from our collaborators spruce seeds, and it appears to be a problem that many of them do not germinate. So they might be empty or they are infested with particular insect larvae. And you can see them in the X-ray image here in the lower left corner. And we got those seeds, and then we imaged them with these two different approaches. I'm not going to show you the computational actual details in here. We were using a classification based on the support vector machine. So basically what we got is that our aim was to somehow demonstrate that is it actually possible to do the same without having 200,000 euros worth of spectral cameras? Can you do it with, let's say, less than 10,000, maybe with 5,000 euros? And we showed that it's possible. And these results that we see over here, the classification on the lower right corner is based on that approach. We selected the best wavelengths based on the whole data and then just used two very simple indices, and we were able to classify them with 95% accuracy. And with spectral cameras, of course, with 99%. Then some wood material science examples, not our work, from literature. One of the things that you can do it in industry is that you look at, let's say in this case, these boards and look for moisture content. And this example, they were using this 900 to 1700. What we have over here is that we have the instruments that actually have longer wavelengths, meaning that they are penetrating deeper into the boards. So we will try this with this kind of material as well. We already did this. This is actually not really related to forestry, but lichens do grow on the forest floor. And here are, I believe, 7 lichen species. This has already been submitted. And we compared the different cameras. On top, we have a normal camera and then 3 spectral cameras. And this is a calculation that is just visualizing where the water is and how much there is water. And there is a range of water content increasing from left to right. So this means that we have a way to look at a lichen and say that, okay, it's 86.2% water. So we will do that the same with wood. Again, from literature, of course, in near-infrared spectroscopy, you can utilize different bands for different chemical characteristics and make maps of these, and we will do this as well. This is some hyperspectral imaging examples where the standard methods are, for example, for density is X-ray, and then some other methods. And you can see that it's possible to make maps for, let's say, lignin content or density or so on, but the pixel resolution is not that good in here. Okay, so early on this year, we decided that let's have some wood from somewhere. We asked our collaborators, give us pieces of wood. Let's see how do they look like. This is one of the first ones. So on the left, normal image, and those are slightly distorted, a little bit too wide images. And you cannot really see the colors well here, but it appears that when we are having narrowband UV illumination, we can see that some of the features are then quite nicely shown. It's not shown as well that I was hoping for. We see, for example, with the blue fluorescence of the different phenolic compounds here, we see a place in the left-hand side, there is a darker band. That is because that particular piece of wood was actually kept on a table, and there was something on top of that. We see that as well. So we also did some UV illumination experiments where we showed that it's possible to see the extent of the color changes in there. Some mid-wave infrared images from a pine, which I'm not sure what the features are, but apparently there are. This was taken yesterday, so we haven't calculated the results yet. And then we have some experiments with collaborators where we are looking at wood decay. So in experiments where we have different fungi, and then we are trying to estimate the decay with the cameras. Now, chemistry is involved, and if you look at the extractives in wood, it says 10%, often it says 5%, but those are most interesting for doing any kind of imaging. And this is a classic example already a couple of years ago from UEF, Keinänen and others did steelbane imaging, where you can actually then have the heartwood detection based on those compounds. And this is important, a slide by Arni Harju, where you can, because it's a good wood quality trait, decay resistance over there, and the steel beams will actually correlate with those. Sorry, you had too many slides. So basically, the motivation for this is that you have to have, if you're going to utilize the hardwood, efficiently fast technologies to do that for solid wood there when you're actually manufacturing these. And now I only have a couple of slides now, 3 images, 3, okay. So thermomechanically modified pine wood, a current thing going on. And what we see over here is that there's one that is not compressed and the other one is thermally modified and compressed. And we can see that there are different fluorescent signals over there and some color differences where we can actually separate. It's not shown here, but we can compute the fluorescent signal being different in the hardwood and then in the knots and in the sapwood in different places. And we are hoping that we are actually imaging steel beams, lignans and lignins separately. And, well, we are throwing everything at these. So different kinds of technologies, again with the same samples, and we can see here the monochrome images are with ultraviolet, really nice for some features, and to see surface features and such defects, but with different kinds of spectral imaging techniques that you can emphasize and make contrasts for some relevant features over there. And this is my last slide. Okay, so group picture, not everyone in the picture. This was made with a pilot spectral camera that we were testing for specking. And outside, we were doing this, and those are the group members that were currently doing this. Lars Granlund, Maja Deepak, Sarita Keskisaari, myself, and Laura Foch. And I will also mention that this private fund, Juho and Lempi Pitkänen fund, emphasized that I should be building now some collaboration with the industry and start research on doing something that industry would be interested in. So that's why I hope that we will have some discussions later on about maybe some possible future projects where we could be then collaborating with you. And thank you for listening.
Thank you, Markku. We have time, only one short question. Oh, it's so. I would like to ask that you have a very nice laboratory and very nice equipment there. So what is missing still? Are you looking for some new equipment?
Yes, everything that I would like to have is so expensive that so probably not anything particular. Although I have to say that Xenop's camera is really interesting. These are heavy, and you cannot put them on a drone. And we have 2 projects starting where you're looking at different things in agricultural fields and also in forests with the drones. And we are currently looking for what kind of cameras to put in there and how much money we can actually get. 40,000, let's see.